Hi everybody, my name is Michael Hanisch, Head of Technology for the DACH region.
And I'm Sascha Möllering, Specialist Solutions Architect for Containers.
And today we're going to talk about how to build reactive systems on top of AWS. And first and foremost, we'll define reactive systems, what they are, and typical use cases. And then in the second part of this talk, we're going to dive deeper and demonstrate how reactive systems can be designed on top of AWS services. And also share an example implementation that you can also find on GitHub for later experimentation. Now let's take a closer look at what reactive systems really are and how they differ from classic N-tier architectures. This is a typical N-tier application. You have a client, typically a web browser, a mobile application that sends requests to a front-end server and waits for a response. And in the meantime, the front-end servers use other APIs, also in a polling fashion, to talk to the backend systems. And behind those APIs are then additional backend systems that rely on yet other components like storage systems, databases, etc. And each call uses synchronous communication. These are all synchronous calls, which of course brings the problem that they're blocking, right? And blocking means that you reduce your throughput, and you also run at the risk of underutilizing the compute resources that you have, which also can translate into higher cost than necessary. You also have tighter coupling, which means that you have location dependence, which also means that it's more difficult to extend and maintain the individual components in this pool-based architecture. Now, requirements for today's applications are often quite different, right? Users expect 100% uptime, no matter how popular or busy an application is. And also, many of today's use cases really require subsecond response times, even when at the same time as data sets are growing into the terabytes and petabytes. Maybe you remember like lectures you've seen on distributed systems and the fallacies of distributed computing, right? Like the network is always reliable or latency is always zero. And as developers are now building systems consisting of hundreds of small software components, all communicating with each other, these fallacies create challenges that become more important than ever, right? And many traditional systems architectures need to be adapted to deal with these requirements. And of course, thinking about what can we do differently, a number of people sat down and in 2014 released the Reactive Manifesto that tries to address these challenges, and it stated a few important principles. Above everything else, reactive systems need to be responsive to user requests and respond in a timely manner if at all possible. And this also requires that the system stays responsive even in the face of failure. So that means that it is resilient. And it needs to stay responsive under varying workloads. So it must be elastic as well, right? And the primary mechanism is that we build these systems using asynchronous message passing to really enforce loose coupling and isolate the components of each other, right? Let's keep those core principles in mind because we'll refer back to them later on. Now, reactive is a word that's often used these days, right? So first of all, there's reactive programming, which basically means that data streams really make up the spine of your application. Events, messages, calls, even failures are going to be conveyed by a data stream. And reactive programming then means that you observe these streams and react when the value is emitted. Using reactive programming alone does not build a reactive system, right? If we look at how the Reactive Manifesto designs reactive systems, you can see that that's really an architectural style to build responsive and distributed systems, right? So you can say that reactive systems are really distributed systems done right. And the foundation, as I've said, is message passing, right? Which creates a strict boundary between the components and allows them to work in a decoupled manner, right? This allows for lots of concurrency in the system, as well as for distribution and mobility. So you can use the services on the other end of the message pipe somewhere else. And this decoupling is also a requirement for full isolation of the components, and thus forms the basis for both resiliency and elasticity. The good thing is that if you couple your systems only in a loose manner, right, you get location transparency, which also means that it's easier to extend and maintain because you can run multiple versions. You can more easily upgrade individual components, for instance, and scale them in and out. Right? Isolation also prevents component level failures from cascading, which also means that you can reduce the severity of failures affecting the overall system. And the non-blocking nature of reactive systems also means that you get higher throughput and have a more efficient utilization of your compute resources, which also helps you lower the overall cost, right? But just keep in mind that the main aspect is that you transform from a pull-based architecture to a push-based approach, right? Where system components push data to their consumers as soon as it becomes available.
At this point, we would like to briefly discuss typical application areas for reactive systems. What all these areas have in common is that potentially millions of events flow into the backend system. So this means the backend system managing all these needs to be able to scale on demand and be fully resilient. In other words, there's actually a need for a reactive system. So a very popular example is AdTech, which is short for advertising technology, and it has the challenge to collect or track a lot of information. So usually you have something like a pixel on a website that does all this tracking, and that ingests data into the system, and depending on the campaign or its success, the amount of data that needs to be collected and transformed can potentially be massive. So in a few minutes we will also take a closer look at an example implementation for a tracking system for ads. Similar for e-commerce, so if you have a product that goes viral on social media or an advertising campaign is super successful, a lot of people will visit the e-commerce website and order products. For IoT, similar challenges, so you have all these connected devices that produces lots of data, so the data need to be ingested, aggregated, analyzed, and maybe also pushed back out to the devices, so the system has to be responsive.
Right. I mean, loosely coupled, right, message passing sounds a lot like familiar patterns for building microservices in general. So can you talk a little bit about the difference between reactive systems and just microservices in general?
Sure. I mean, usually people often mean different things when they use the term microservices. So in this talk, we will define microservices basically as an architectural and organizational approach to software development designed to speed up your development cycles, foster innovation and ownership, and improve maintainability and scalability of the software application. And reactive architecture or reactive microservices architecture is a specific type of microservice architecture. So this means we have the reactive property that enables the service to be elastic, so the compute resources can scale up and down on the cloud depending on the amount of data. And resiliency, so if a node fails, it can self-heal. And being responsive, so you have high availability and low latency. And the key to reactive microservices is, as already mentioned, asynchronous message passing between those microservices. We've taken a closer look at how reactive systems are defined in typical use cases. Now let's find out how we can map the 4 reactive paradigms, being responsive, resiliency, elasticity, being message-driven, to AWS services. And we picked only a subset of these AWS services, namely those we use to implement our example architecture. So reactive systems need to be responsive. That means they need to respond in a timely manner, which is we need to reduce latency. So we're using 2 kinds of compute here. So we have Amazon Elastic Container Service, or ECS, as well as AWS Lambda. And we use containers and Amazon ECS to host then the main application that ingests data streaming with minimal latency. So we do not want to invest too much time into running this infrastructure and this application. So we make use of AWS Fargate to manage everything below the containers for us.
Right, so why use ECS and Lambda? Right.
So the main application basically implements the real-time part of the architecture. So usually in AdTech you have a few things that need to be done in real time and some things that can be done later asynchronously, which means we want to reduce the latency as good as possible. And that's why we've decided to combine all parts that are necessary in a containerized Java application using an asynchronous or non-blocking framework to use the compute resources as efficiently as possible that we have. And we just want to focus on the application and not the underlying infrastructure, and that's why we've picked Fargate as a launch type. And to consume messages from Amazon Kinesis data streams, we've implemented Lambda functions using Golang to read the data, transform it, and store it in DynamoDB and Redis. And when it comes to resiliency with AWS Fargate, building resilient applications is actually quite easy. So you do not have to worry about things like task placement strategies such as bin packing or host spread, and tasks are automatically balanced across availability zones. So and Fargate manages the availability of containers for you. Lambda scales automatically and runs functions in multiple availability zones, so it's a regional service. So and this ensures that that it is available to process events in the case of service interruptions in a single zone. And each function invocation is also isolated from other executions, which reduces the blast radius of failures in the function code. And for the low latency data access, we rely on Amazon Elasticache. And in certain cases, Elasticache for Redis detects and replaces a primary node. So if you have multi-AZ enabled on the cluster, the downtime is basically minimized. In this case, the role of primary node fails over to one of the read replicas. So there is no need to create or provision a new primary node. And this failover and replica promotion ensures that you can resume writing to the new primary as soon as promotion is complete. And for our persistent data store, we have chosen Amazon DynamoDB. DynamoDB synchronously replicates data across 3 facilities in an AWS region, giving you high availability and data durability. And ECS publishes CloudWatch metrics with your service's average CPU and memory usage. So you can use these and other CloudWatch metrics to scale out your service, so which means you can add more tasks to deal with high demand at peak times, and to scale in your service, which means running fewer tasks to reduce costs during periods of low utilization. In addition, we are relying on AWS Fargate to scale the underlying infrastructure for us. So this means it will automatically add or remove new hosts that ECS runs our containers on. And every time an event notification is received for the function, AWS Lambda quickly locates free capacity within the compute fleet and runs your code. Since the code is stateless, Lambda can start as many copies of the function as needed without lengthy deployment or configuration delays. DynamoDB automatically scales throughout capacity to meet workload demands and partitions, and also repartitions your data as your table size grows. Reactive architectures are message-driven, and we decouple the real-time part and the persistence part of the data from each other using Amazon Kinesis data streams.
So why use Kinesis data streams over, let's say, SQS or Kafka, for instance?
Good question. So for this use case, it was important to have the option to replay events. So if something goes wrong with the data was corrupted, so we just wanted to replay all the events, which means SQS wasn't really an option, but Kinesis and managed streaming for Kafka. So in this architecture, we wanted to focus on the application development, and Kinesis data streams is super easy to use and also has great Lambda integration. And in addition, we have Redis pops up as a mechanism to push data to different instances of the main application.
So why use both Kinesis data streams and Redis pops up, right? I mean, both are fairly different in terms of durability, for instance, and other properties.
Yeah, so one of the main design goals was to reduce the latency as good as possible. And Redis is used as a caching layer on top of various other data sources, or can be used for this use case. And we have implemented also a 2-level caching strategy. So we have an L1 cache in memory in the main application, and then we have an L2 cache in Redis.
Right. So let's talk about an example use case to make this a bit easier to understand, maybe.
Sure. So let's assume we work in the AdTech industry and we want to build a tracking system. So you visit a website, and then the banner, for example, for shoes are shown, which is usually paid by the advertiser, in this case a retail store. So you click on this banner, which redirects you to the shop, and this is the part that needs to be done in real time because it can have an effect on the conversion rate. So this data has to be tracked, and you need some kind of real-time data ingestion and validation mechanism because you have to check, is this a valid advertising campaign, and so on. So then you buy the product, and this information will also be tracked. Then you have the match between the click on the banner and the checkout of your shopping basket, and this is then used to charge the advertiser and distribute the money to whoever is running the website we initially started with. And this is called affiliate marketing. So if you want to dive deeper into this example after the talk, you can have a look at the reference architecture link below, and it comes with an AWS CloudFormation template that sets up the complete high-level architecture component and also the sample application.
Right, so let's take a closer look at the high-level architecture, right? And each of the components that we use in this architecture, but as well as the communication path between them, right? As already mentioned, we'll keep discussing the patterns for reactive architectures in the context of our overall architecture to show where we implement resiliency and elasticity. So we start again with like our client that sends in the request, let's say from a mobile app, from a web browser, that hits the application load balancer, which is hosted, it scales automatically, and it just forwards the request into our application, right? That runs on ECS, right? So it's fairly responsive, implemented in a non-blocking fashion. It runs compute of our application and then puts the event into the kinesis data stream just to store it and to decouple it. And then on the other side of the stream, we have this Lambda function that basically gets the new data as it is pushed into the stream. It scales up or down automatically, right? We've talked about those properties. Transforms the data as needed and then stores it into DynamoDB. Now, of course, our application does not just use the data that comes in from those tracking events requests, but you can also use other data, which we've defined as core data, such as, for instance, the name of the advertiser, whether there is a running campaign, whether it has been paid for, etc. And we basically put all of this core data into Elasticache Redis just to really reduce the latency that we have. Of course, there can be various systems where this core data is actually stored that produce updates on this core data. And to decouple those as well, we ask each of the core data systems to push their updates via kinesis data stream, right? So we really have an asynchronous decoupling. And then we have another Lambda function that can consume all the various events from different backend systems, reformat them as necessary, and then put this into our Redis data store, which kind of like acts as a facade to all the other data sources that we have in our backend system. So we really have decoupled both the real-time part that has events flowing in and the core data updates that are processed at a different time scale.
So in the last few minutes, we took a closer look at the high-level architecture of the application. And in the following, we'll dive deeper into the individual components and take a closer look at important design decisions and also patterns. So the main entry point for the traffic in our architecture is, as you've already mentioned, the containerized Java-based application running in Amazon ECS with the AWS Fargate launch type. And we'll take a closer look at how the application is actually implemented. So we use many different design principles in our system architecture to decouple the microservices from each other and to use our resource pool of compute capacity as efficient as possible. So first of all, we switched from pull to push in order to reduce communication with our Redis cluster. So we get notified if core data updates are available. And by using asynchronous and non-blocking frameworks, in this particular example we've used Vertex, we can avoid blocking calls. And by decoupling our service using asynchronous message passing with kinesis data stream, we can basically use the same patterns in our main application that we also use on a macro level. So let's say we have internally in our main application the Vertex event bus that decouples components of our application from each other, and we have the same principle on the macro level of the whole architecture. So we also keep the state in managed services like DynamoDB, Kinesis, and Elasticache, and we use this two-level caching strategies with an in-memory L1 cache and Redis as an L2 cache to reduce latency. So this means the same principles apply to our application architecture that also apply to our infrastructure architecture. And for this example, we've picked Vertex. Of course, you can basically do the same or very similar things and implement the same paradigms using, for instance, Akka or other frameworks. And Eclipse Vertex is a toolkit for building reactive applications on the JVM. And it's event-driven and non-blocking. This means your app can handle a lot of concurrency using a small number of kernel threads. Vertex lets your app scale with minimal computing power. And it comes with a very simple, scalable, and actor-like deployment and concurrency model out of the box that you can use. And Vertex uses event loops. And in every event loop is attached to a thread. And by default, Vertex attaches 2 event loops per CPU core thread. And the direct consequence of this pattern is that a regular vertical always processes events on the same thread. And each event shall be processed in a reasonable amount of time to not block the event loop. So this means that all thread blocking operations, which could be access to a file system or JDBC call or something like this, shall not be performed while executing on the event loop. And a vertical can be passed some configuration because you need, for instance, credentials, network addresses to access external systems. And the vertical can be deployed several times. So this is really important. This is inside of your container. So you have a fine-grained mechanism to scale your application as well. So you can scale on multiple layers here. And incoming network data is basically being received from accepting threads and then passed as events to the corresponding verticals. And when a vertical opens a network server and is deployed more than once, then the events are being distributed to the vertical instances using a round-robin fashion, which is amazing if you want to maximize CPU usage with lots of concurrent network requests. So we see here we use the same architectural principles in our application as for our high-level architecture. And just to show a quick example here, verticals basically form technical units of deployments of code in Vertex. And the Vertex event bus is the main tool for different verticals to communicate through asynchronous message passing. And here we have one vertical that deals with all the HTTP requests and a vertical that manages access to our Redis cluster. And the event bus allows the HTTP vertical to send requests to the database vertical that performs queries to our Redis cluster and then sends back the results of these queries. And you can basically pass any kind of data, and although JSON is basically the preferred exchange format since it allows verticals written in different languages to communicate. And the caching layer abstracts all our core data, no matter where it's stored. So we always get updates and modify the data in the cache accordingly. Aside from the updates to the external Redis cache, and our application also keeps its own L1 cache. And of course, whenever this Redis cache is updated, we need to update our in-process cache as well. So going with our design principles, we want to get updates pushed into our application. And we use Redis for that because it's a very fast and lightweight implementation of PubSub. And we use this in our application because we already leveraged Redis for caching purposes, so as some kind of database replacement. Of course, it would be possible to use different PubSub implementation like Amazon SQS and Amazon SNS, but we wanted to keep the set of necessary services rather small. So in addition, Vertex offers great support for Redis PubSub. So this means core data changes are distributed to the instances of our main application using Redis PubSub, and if data isn't found in L1 cache, a lookup is done in Redis. So this means durability isn't that important in this particular case. So, and to illustrate how the PubSub works in the context of the main application running in ECS, let's take a quick look at a vertical that is responsible for the whole communication with Redis. As already mentioned, vertical instances communicate with each other by sending messages on the event bus, which means we have to subscribe to the event bus in order to receive messages. So first of all, we have a code snippet here where this particular vertical subscribes to the event bus. Then we have a Redis client subscribing to the Redis channel. So these are two different steps, and these are really important. Then we send our data over to our vertical using the event bus, and we consume the data in our vertical, unwrap it, and send the data to our caching vertical. And after diving deeper into the main application, we'll take a closer look at one particular Lambda function. And this function reads data from the Kinesis data store, unwraps the binary data, and stores it in Amazon DynamoDB. And we've used protocol buffer for serializing structured data. And protocol buffer is really amazing because you can have a service contract with built-in validation, which is great if you have a polyglot architecture with different frameworks and languages and so on, which you have used to implement your microservices. So in this case, the main application is written in Java, and the Lambda function is implemented in Golang, so we have this service contract validation built in, and we don't have to implement this. AWS Lambda is basically serverless compute. And Lambda runs your code without provisioning or managing servers. So you pay only for the compute time you consume. We already discussed stateless or being stateless. But what does being stateless mean in the context of Lambda? So usually for applications you have states like user sessions, and this should always be stored in services like DynamoDB or S3. And Lambda functions execute in a container, which is kind of a sandbox that isolates them from other functions and provides the resources, such as memory, specified in your function's configuration. And this container exists for a certain amount of time, so please don't assume any affinity with the underlying compute infrastructure, because let's say you store files in /temp or so in your Lambda function. In the next call of your Lambda function, this may be gone, because it could be the case that this call directs to a complete different Lambda host.
Right. So now we've hopefully explained why reactive architectures are a very good fit for AWS and what reactive systems really are, right? How you can improve isolation of components, how you can reduce latency. And we've looked at a couple of AWS services that allow for this decoupled application design, right? Like Kinesis data streams, for instance. We've also looked into a bit how the same architectural principles are really represented on the micro level, like with the different verticals communicating with each other in a loosely coupled way, how caching is being used, right? Just to give you an idea of how these architectural principles really go through the entire stack. Now, we've only talked about a few services, but you've hopefully seen how you can use those to automatically get properties like resiliency and elasticity built into the service, right? And the idea, of course, is that you don't have to do the things of your own, right? You don't have to reinvent the wheel all the time. You should really focus on your business requirements. And now, hopefully, you can go ahead, try out this CloudFormation template, start the reference architecture, which will then launch all the different components, install the application itself, so you can explore further, right? And we've listed a few resources on this slide. For instance, a blog post that talks you through the architecture in a bit more detail, and of course the CloudFormation template. There's also some resources on Vertex, for instance, but also for how to minimize the containers that you use, just to reduce the footprint of your application further. And of course, general architectural principles like the well-architected framework still apply, right? So it always makes sense to check these out and have a look at other solutions and reference implementations that we have available for you. Yeah, so we say thank you very much. We're at the end of our talk.
Thank you very much.